Have you ever really stopped to think about what happens when you hit send? Well, we're about to pull back the curtain on the internet and follow one single piece of your data on its absolutely epic split-second journey across the entire globe. It's something that happens billions of times a day, and the mechanics behind it, they're just fascinating.
I mean, think about it. You tap send on an email, a text message, whatever, and in what feels like less than the blink of an eye, it just arrives. So what's actually happening in that tiny fraction of a second? It isn't magic, you know? It's an incredible, high-speed technological relay race. So let's break it all down. All right, so our data packet's journey starts the very moment it leaves your device. This is step one, just getting from your hand into the local network. Now that could be your Wi-Fi at home or the cellular network when you're out and about. Okay, let's say you're on your phone, maybe walking down the street. You're constantly moving from the range of one cell tower to another. To keep your call from dropping or your video from buffering, the network does this seamless little trick called a handover. It passes your connection from one tower to the next, and you never even notice. It's the first of many, many handoffs for our little packet.
Now, once our packet gets inside a bigger local network, think a big office building or a university campus, things need to be kept tidy. That's where something called a virtual LAN or VLAN comes in. What they do is take one single physical network and digitally slice it up into separate pieces. It's a brilliant way to keep, say, the accounting department's traffic from jamming up the engineering department's network. It's all about keeping things organized and efficient.
So, our packet has officially left the local neighborhood. Now for the hard part. It has to find its way across the entire world. This is where routers come into play. You can think of them as the traffic cops of the internet. And they have this absolutely colossal job of figuring out the best possible path for our packet to take, out of trillions of possibilities. No big deal, right?
So how do they do it? Well, routers build their maps of the internet using two main strategies. On one hand, you have link state. With this method, every router gets a full, perfect GPS-style map of its immediate area. It's super fast, but it can be really resource-intensive. On the other hand, there's distance vector. This is more like asking for directions from your next-door neighbor, who then has to ask their neighbor, and so on. It's simpler, but it can be a lot slower to react if the network changes. So two different approaches to solving the same puzzle.
Now here's a key thing to understand. The internet isn't just one giant network. It's actually a massive collection of huge independent networks. We call these autonomous systems, or ASs. A great way to think about an AS is like a country's national postal service. Your mail moves around really easily inside that one country, but to get a letter from one country to another, well, those two postal services need to cooperate.
And that brings up a really important question. How do these giant independent networks actually talk to each other? How does a data packet know how to get from, say, Comcast's network in the United States all the way over to Deutsche Telekom's network in Germany? They have to be speaking the same language. They need a master protocol.
And that special language is the Border Gateway Protocol, or BGP. You can think of BGP as the official protocol that literally stitches the entire global internet together. It allows these huge networks to tell each other which addresses they can reach. It's basically the master map of directions for the entire planet. Without BGP, there's no global internet. Simple as that.
Okay, so our packet has its global travel itinerary. Now it's time to hit the fast lane, the high-speed fiber optic superhighway that is the internet's backbone. And out here, every single nanosecond counts. Just imagine a busy mail sorting facility where every single worker has to stop and read the entire, long, complicated address on every single letter that flies by. It would be an absolute bottleneck, right? Incredibly slow. Well, that's kind of the problem that traditional routing faces on the internet's core network. It's just too slow.
The solution to this problem is a genius trick called multi-protocol label switching, or MPLS. Instead of making routers read the whole complicated destination address at every single stop, MPLS just slaps a simple, short shipping label on the packet. Now, the core routers only have to glance at this super simple label to know exactly where to send the packet next. It's so much faster.
And the process itself is just beautiful in its simplicity. When the packet enters the superhighway, an entry router pushes the first label on. As it zips through the core, each router just swaps that label for the next one in the path. Then finally, when it reaches the end of the express lane, the exit router pops the label off, revealing the final destination address for the local delivery. It's push, swap, pop. Done.
So this system is incredibly fast, really slick. But all that speed was built on a much older foundation that was starting to crack under the pressure. See, this amazing system had a huge fundamental flaw. The original addressing system was simply running out of room. With the absolute explosion of internet-connected devices, we're talking phones, laptops, watches, servers, everything. It created this kind of digital real estate shortage. There just weren't enough unique addresses to go around. People came up with some clever, temporary fixes, but they were pretty inefficient, and really they were just kicking the can down the road. A much bigger solution was needed.
Yeah, it became really clear that we couldn't just keep patching the old system forever. The architects of the internet had to think way, way bigger. They had to design a completely new foundation that was ready for future growth.
And that solution is IPv6. Its main advantage is almost laughably simple. It offers a massively, almost unimaginably larger address space. We are talking about a number of addresses so big you could give every single grain of sand on Earth its own IP address, and still have trillions and trillions and trillions left over. So yeah, this pretty much ensures the internet has room to grow for a very, very long time. Okay, our packet is getting so close to its destination. It has crossed continents, it's navigated these super complex networks, and it's using the next generation addressing system. But there is one last, absolutely critical step, making sure it arrives safe and sound.
And this is exactly where virtual private networks, or VPNs, come into the picture. A VPN basically takes your private data and puts it inside its own secure, encrypted tunnel that travels over the very public internet. It's kind of like putting your important mail inside a locked metal briefcase before you hand it off to the postal service. Nobody can peek inside.
The technology that builds this digital armor is often something called IPsec. It's what establishes that secure, managed tunnel, and it handles all the heavy lifting of encrypting your data. It makes sure that even if someone could somehow intercept your packet, all they would see is a bunch of scrambled, totally unreadable nonsense.
And our packet has arrived. Safe, sound, and all in a tiny fraction of a second. So let's just take one final look back at this incredible, invisible symphony of technologies that made this whole thing possible.
I mean, you start with the humble VLAN, just keeping local traffic organized. Then you have the global map making of BGP. You add in the raw speed of NPLS on the backbone, the practically infinite space that IPv6 provides, and finally, the protective shield of a VPN. Every single piece plays its own critical role in this seamless journey.
And this whole complex dance, it's happening billions of times a second, every single day, all around us. It is the invisible circulatory system of our modern world. So that leaves one big question. What's next? As our world gets even more connected, what new challenges and what new technologies are going to shape the next stage of this incredible journey?